no. Oh, no, 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 no. You guys can't see that yet. You can't see that yet. That's not done. So, to start this video, I want to say that this video is coming out like, it was filmed like, I don't know, a month ago. A long time ago. And in that time, I've been working on the Mark I, and I still have a ton to do on it. And I've realized something. Even though I'm done with the broad strokes on the Hacksmith power armor, I still have a lot to do. So there's this thing called the 80-20 rule, and the last 20% takes 80% of the time, and that's definitely true, let me tell you. I probably have 3 more weeks at least to refine that, but I'm not going to be working on that for the next 3 weeks because I still have stuff to do on the Mark I. So I just want to let you guys know why this video came out late. Well, the reason it came out late is because I'm lazy, but also to give you an idea and to set your expectations correctly for when you can see the finished Hacksmith power armor. And with that, I'll send you to the video. Bye, guys. Good morning, everybody. Today is a special video because it's like pretty much the last video on this series. I may do a shorter little video kind of explaining some of my failures in the manufacturing process and send that to James. Okay, let me start at the beginning. This video series is about my videos to James Hobson, the Hacksmith, who is both doing me a huge favor by helping me out and helping my channel, but I'm also building him an exoskeleton. And this is me explaining the design to him because it's much easier to do that with like visuals and stuff instead of trying to type out emails and things. And you guys get to watch it too, so that's exciting. Today's the last video. I put my SR-71 Blackbird. Can you see it right there? Yeah, I just wanted to show you that. Okay, let's take a look. Today is actually kind of a cool video because it's, I think, probably the coolest thing I've ever made. I forget to look at the camera. I'm looking at the monitor, looking at you. I think it's probably the coolest thing I've ever made. So this is how I view Fusion 360 because the bright lights hurt my eyes. But we're gonna take it and we'll put it into photo booth so that you guys can see things better. So remember, if you haven't watched the earlier videos in the series, this is a scan of me, but I've resized the scan to be about roughly 3 inches taller. James is taller than me, so this should fit his body perfectly. Yeah, my lava lamp's not going. Bummer. Last video and the lava lamp doesn't work. All right, here it is. This just turned on. So let's take a look. Let's take a look. I'm gonna turn off the scan really quick, and I'm gonna turn off this entire side. So this video is mostly gonna be about the arm. There's gonna be a little bit about the leg, but the arm is a much more complicated version of the leg, so we're gonna focus mostly on that, and I'll show you the leg briefly at the end. But this is the arm right here. And I think the best way we should talk about is we should go through and I'll show you every single joint on how it moves, and then I'll show you how it's powered. So, because this one's gonna be fully powered. This has definitely got the most power of any other part of the suit. And when I say powered, I mean like actuators. So I'm gonna come in here, I'm gonna drive the elbow joint, and we're gonna see how it moves right there. So there's that. Now, actually, I think I am going to talk about this actuator really quick because it's pretty obvious as we talk about it here. This actuator right here is going to be a hydraulic piston. There's actually that James can get in Canada. There's a shop next to him, and I sourced one of their actuators. So this one is going to produce a lot of force. Do we want to talk about how much force it's going to produce right now? Let's do it since we're right here briefly and talk about it. So, high school algebra in force equations too. Torque, sine, theta, force times radius. That's what a torque is, right? So the torque is constant over this joint right here. So you can take it and you can set the sine theta of the bicep, which is the hydraulic actuator, times the force of the bicep times the radius of the bicep equals the sine of the force of the hand. So we're solving for the force at the hand. Times the force of the hand times the radius of the hand. Rearrange for force at the hand. Also sine 90 goes to 1 because we're going to assume perpendicular to the hand. And I have let's see here. So I have here this is a much earlier sketch, so you can see I don't have the front of it done yet because I was doing this at the beginning, but you can see all of my my two radii right here, there's your angle 90, and then this is your other angle, right? And so this is at straight, and so that's the arm pretty much at full extension. I think not quite full extension. Oh, and I have another one in there for it bent, but I can't find it because I forgot to name it, and there's like literally 100 or like, yeah, over 100 sketches on this thing, so I can't find it. But this is kind of how I like to do things. When I'm doing a lot of force stuff and I'm changing numbers often, I like to put them in a spreadsheet so I don't have to keep typing them into a calculator. But this right here is the force, this force 2 is the force at the hand that we were solving for. This is the force produced by the actuator, 2,000 pounds. And so this is the force felt at the hand. So at full force, when the arm is straight, 70 pounds, but that's not bad because James has some strength too. And once getting it that started is usually the easiest part. It's like in the middle of a curl, right? Like halfway through a curl is when the force needs to be the highest, and that's the force there is 273 pounds. I'm pretty sure the suit can handle that amount of weight because I've redesigned some parts of it. At first I was only designing for 200 pounds total, but we might be able to pull this off, but we can always underpower the actuator, the hydraulic cylinder as well too. But a lot of force. This is just one arm too, so you'd be at like strict curl 600 pounds, which is insane. I gotta double check that the suit can handle that, but I know the arms can handle it. I'm talking about the rest of the suit, if it's gonna bend metal in the rest of the suit. But that's how that works right there. I'm just gonna show it to you one more time. One more time here, you can see how that is shortening right there and pulling that up and then pushing it down. So there's that. And then the next joint is gonna be pronation and supination of the forearm, or I guess the wrist. Those are technical terms. I studied sports medicine in school, so sue me, I don't know. But let's go on to the next one. So this one right here goes like that. Oh, and that is not supposed to spin like that. I gotta change that in the model. This is supposed to be a fixed part. Let me turn that off. Okay, this gear right here has a cover over it that I didn't add, but there it is moving right there, right? So moving around, obviously it would stop, it wouldn't go all the way around. But this is a geared system. I just used a gear maker right inside of Fusion 360 to do this. It's pretty cool, right? So that's gonna be powered, and it's gonna be a brushless DC motor, which is in that thing back there. If you're curious what that is a hydraulic power unit that I made for my exomuscles. It's gonna be the same type of motor that similar, very similar to the type of motor I sourced for that one. So essentially what you do is you have this gear here, and it's a gear reduction, right? Which will give this more power here, more torque. Be a little slower, but it gives it more torque. And then on the end here, which I don't have modeled yet, but which is okay, because we don't need to build this until it's powered. But this piece that goes over it will then have a part bolted onto it, and that part bolted onto it's what's called a rotary encoder. They're generally like the same kind of things that you use to turn the music up in your car. If they just click and they go around, but probably one with higher resolution. And there's this thing called an O-Drive, which is an open source board that I've used before, and they're fairly easily user-friendly. I mean, it's a little bit to figure out, but they're not too bad to use. And essentially, you take just a brushless DC motor off the shelf, and then they'll actually send you a rotary encoder. You just stick it on there, and it pretty much works. You got to put in like the number of poles of the motor and stuff on it, but it turns your motor that's normally just for like a skateboard, right? For like spinning really fast and just doing things with a lot of power. Now you have high positional control over it, and you can essentially turn it. You can essentially turn it into a AC servo motor, which is like what drives those big industrial robots. So that's cool. So that is that's how that's going to work, and then it's also going to be important to have that rotary information to know the position of the hand, because I'm planning to use that to control the bicep as well. I'm going to get to that in a second. But let's get to the cool part, which I'm sorry it's taking me like 8 minutes into this video to get to the cool part. But this is the hand, and this is like the most, I think, complicated part of the suit. It took me a long time to build. I'm pretty tired right now, but let's look at it here. So the first joint is this joint right here, and it's one of those double joints that I've used before to give you a higher range of motion without making the joint huge. But it spins down, and that allows your wrist to go down and up like this. Do that a few more times for you guys to see, like that. There we go. Pretty darn cool. I'm gonna put my body back into the suit really quick so you can kind of get an idea where the hand is going through there, right? So this is spinning around a point right here in the hand. And then the next one after that is this joint right up here. And I might just be able to grab and drag, yeah, there we go. So that one right there is side to side like that. So you have those are the two ranges of motion you have. You can't spin your wrist, well, you can't spin your wrist, that's done up at the top. So there's three, I guess there's three axes of rotation for your wrist, right? Right there. Now it starts to get a little bit fun. So let's go to the thumb first. Thumb is a little bit hard to see, but up underneath here is this joint right here, and there's the joint attaches right down here, and there's two joints. It's called a saddle joint. It literally looks like a saddle that the joints do, and if you look at the bones, but you got one joint this axis this way and one axis this way, and so the same thing is true here. So there's one this way right there. Let me zoom out a little bit. There's one this way right there, in and out, in and out, in and out. And then there's another one hiding in here, and it was very difficult to get these not to interfere with each other. And they will probably touch a little bit in certain extremes of the movement, but that's okay. And then the other one is side to side like that. So you have 2 degrees of freedom there, like that. The thumb isn't powered, but it'll be armored. And any load that is holding it will go through the suit, I suppose. And then obviously what you may more think of is like these two. So these two joints in here are essentially what allow you to do opposable thumbs. That's essentially opposition of the thumb, those two joints right there. So there's one there, and then there's another one here. And I took a lot of time to make this structure very strong because some of my earlier designs of this had it being like just little tiny pieces of metal, and I didn't like that. I wanted this thing to be very robust because it's like the weakest part of the suit, right? So I made it as strong as I possibly could. So that allows you to bend your thumb down, right? Cool stuff there. Now we're gonna get though into what I'm really excited about, what I think is probably my, I don't want to brag, but it's like my best work. And then it's kind of weird. It's like I was working on this so much, it kind of felt like it wasn't even me working on it anymore. Like it was like some other being doing work through me. I worked a lot on this. This took a while to get done. But there's one motion there. And so these are just allowing you to curl your fingers down there, bam. And the motion is not necessarily that cool, but how it's powered is what's so cool to me. So there's that right there, there's another one right there. And then one more right there. So that's curling your hand into a fist, right? Cool. Iron Man, power armor's definitely got to be able to make a fist. So now I want to talk about what I really want to talk about, which is how it's powered. So let me turn off some things here and turn on some things here. So these pieces of brass, and the reason they're made out of brass is because I want them to be as slippery as possible. And like brass, for like all the metals you can get, it's kind of got its own like lubrication properties to it, which is kind of cool. Excuse me, it's early, I need coffee. But the reason for that is that there's gonna be a Kevlar tendon. I should have brought down my suit. Should I go grab it? Hold on. So this guy right here is one of the first exoskeletons I made. It's actually still the most popular video on my my channel too. But this, you'll actually see how like remarkably similar the upper bot, this part is up here. This joint's a little different, but the rest of it's pretty darn similar. But this Kevlar, the hand changed a lot. The hand was goofy, but this Kevlar, this thickness of Kevlar is what I modeled for, and this is pretty strong Kevlar. I think it's rated for pretty high loads. Is the Kevlar? It's just Kevlar string. They use it for like crazy fishing line. is what I'm using on this. So what happens, the thing about Kevlar is even though it's really strong, it can shear pretty easily. So like if you take Kevlar, like a bulletproof Kevlar vest also has to have something else in it, like metal or something like that, in order to stop a knife. So you don't want it to cut. So the Kevlar has to be pulled around things that are very smooth or round or whatever. And so that's what all these little lathe bits in here are. So the Kevlar string, I'll talk about where it comes from, but it's gonna come through this channel and then through this, and then it's gonna start to wrap around through here, up through here, up through here, here to here, and then there'll be like an aluminum ferrule or something that gets hammered on the end and held there. And what's nice about particularly the cutoff for this is if you watch people like on YouTube have made videos about like how to swing like Spider-Man from Kevlar, and they use this type of string, but it breaks if you like wrap it around something tight. Again, back to that cutting thing. So what's nice about having this on a loop is that it won't create a shear, like a point, essentially a stress riser is what they call it in engineering. It'll keep that from happening and breaking, right? So that's part of that too. So the question is like, does it work? So let me come over to the other side. I'll turn the tendon on here. Okay, so now what we're gonna do is I'm gonna snap this forward, and I gotta turn this off really quick. So now this is what it will look like when it is bent. So here is the path it'll take, and you can see it actually at the very extreme of the fist being made. It just bypasses this one altogether, which is totally fine. And by the way, I should say the gap in here is so small this cable can't get out, which is important to the function of this, right? And all these parts have like little lips on them. They have little lips on them to keep the cable from coming out. But if you add up, another way to think about this is if you add up the length of this, which I did, because I need to know how much it's contracting by. The length of this cable versus the other cable, which I'll add back up here. This is where it would be if it was straight, right? That length is shorter by about 2.5 inches. It's fairly substantial. So that's how it'll wrap. So if you pull on this, it'll cause your hand to contract. So we're gonna go back here, there we go. And then this cable would then come and run through these lathe pieces here. And I need to add big fillets to the corner of this because I want that to be nice and round so it doesn't cut it. But it come through this kind of like a bike tire, or a bike brake, excuse me. And then come into here, and then come into this thing, which is a swivel. It'll swivel around that, still out of brass. That might not be 100% necessary, but swivel around that and then attach to these linear actuators right here. So these pistons right here, and these should be, they could be pneumatics, that's possible. But right now I have a model that after some hydraulic ones. So these things will push forward, and then as those push forward, it'll pull that cable down. And if it's hydraulics like James, you could literally like maybe have like hundreds of pounds of force in your hand. I mean, you could literally make a video, perhaps. I mean, we make a video about powering all of it, but if we could just do this, like you could maybe like crush a melon with your hand or something like that, it'd be pretty cool. And yeah, and then there's one going out the other side. They kind of flange off to the side, which is kind of cool looking. It's nice because it'll be flat and your arms can still sit against the body. They're not like sticking out where your arms like have to rest out like this. Yeah, it's pretty wild. Let me look at my notes here and make sure I got everything right. So the one thing I want to talk about, I was showing this to my parents, and my mom walked up and she's like, "That's really cool. How's it gonna know when James starts to move?" I'm like, "Oh, you're right." Like, I gotta make sure I can do that. So there's two things. One of them is we're gonna put an EMG sensor on James's forearm. So when he grabs his arm, when he grips, that'll sense that, and that'll turn the two hydraulics on. And that's pretty easy. Then if it's not on, it just turns off, and then or just goes back the other way, and then everything's loose and can move around. So you can have some threshold over which if James is squeezing over that amount, that turns on. That one's pretty easy. The more tricky part is how do you control this piston? Because that piston, if it's not on, James can't move his arm. Because you can't force a hydraulic piston to move. They're too much force, especially with this type of moment arm and stuff. It's not gonna happen. So I'm pretty sure it's not gonna happen. It wouldn't happen quickly, that's for sure. So what you want is, you have to know where James is pretty much at all time, or he's gonna be locked into position. So, which would be fine for like a quick video. If you just wanna lift something heavy, you just put it on and you pick it up. But I would like you to be able to actually move around in this thing. So what we're gonna do, what the plan is these holes in here, and I'm pretty sure these will work. Like, yeah, they'll work. But I have to design something that's gonna come in and then bolt around from both sides. And then I have some clever ideas on how it's gonna kind of connect up top too. And I've done some stuff like this in my exoskeleton, but and I haven't modeled it yet because it's gonna be fairly complicated. But what it is, it's gonna have a bunch of tiny little pressure sensors. And there you can get some pressure sensors that are literally just a sheet. And then I'll squish them between two pieces of metal, and then I'll have like some rubber facing towards James's flesh. And they're around the bones, so you should get good positional accuracy. It's not like around super squishy stuff like your forearm or your bicep, which is changing shape every time you flex and stuff. Your bones are staying the same shape pretty much the entire time. So put these pressure sensors on there, and then add up all the pressure sensors, and then based on the feedback of this rotary encoder, you'll know the position of the forearm, and then we'll be able to work out if your arm's twisted like this and you have force on this part. Obviously we know that the arm wants to lift up, but then conversely, if it's like this and you have force on the backside, it feels up, it pulls, it wants to lift up, and vice versa for going down. So that's the theory. Obviously this thing would be, if you just did like an if-then statement in the code, it would be really jerky. So the best way to do this would probably be an artificial neural net, which is what I want to do eventually, but that's really complicated stuff and requires huge data sets, which we don't have. So the best way to do this is to use a PID control, which is the type of control that they use for drones to fly, essentially. And it should be a pretty simple PID to write. And then essentially, once you figure out the kinematics of where the position of the arm is, it should be a fairly easy PID loop to write for controlling of the bicep. It's a little complicated, but I think it's just doable. Yeah, that's pretty much the theory for how that's going to work. I haven't modeled that support yet because it's going to be pretty complicated, and I just haven't done it yet. But yeah, that's what we're looking at there. Cool. So I'm going to flip over and show you the leg really quick, which is a little less complete, but is also pretty cool. So here's the legs right here. There's me inside of it, or I guess James inside of it. I keep saying me because it's a scan of me, but it's really James that's going in there. So there's that. I'm gonna turn it back off really quick. This is a lot simpler, but it's also very similar. So into this cavity right here will be another hydraulic cylinder, a bigger one, for a bigger range of motion, also just to fit too. But I haven't modeled that one in there. I realized I forgot to do that as I was starting this video. I'm like, oh shoot, I forgot to model that. But anyway, there it is right there. Let me drive this joint. So here is the knee joint right there. So that's bending the knee like that. It'll stop actually right about there. So I might need to adjust a few things in here. That's probably, I realize I haven't done all the force analysis on this yet either. So I got to do that, but got the broad strokes done here. So I'll get it up to where the knee can come to about 90 degrees. So that's the motion in there for the knee. And then one axis of rotation that has given me, it's probably some of the hardest stuff to figure out, and I haven't been quite able to figure it out, so I just left it out, which should be okay, is the internal and external rotation of the knee. So you can only do that though if your knee is bent, so you're only losing that axis during certain movements, if that makes sense. That would be the ability to turn your toes like this, but you can do that from the hip, which is how your body does it if your knee is straight, but then if you bend your knee, you can still do that. You won't be able to do that in this suit, so just something to keep in mind. It's the only axis that I don't really have modeled in the suit. So let's go down to this one. So this is the ankle joint. This is probably my favorite joint in the suit. This is like the suit, when I made it in my suit, brought a huge grin to my face because it worked so well. These parts, because of all the load on them, they have to be polished so they slide cleanly, but once you do that, they glide around like silk. It's pretty awesome. So this allows, so like you can see, honestly, that might even be too far. I might want to change that because if your foot gets that straight, I guess it can get that straight. It's not the end of the world. Probably would run into itself though. Let's see. I feel like it's going to run into the Achilles tendon. Yeah, it's going to chop your tendon. So I actually probably could reduce the size of this joint a little bit to where it would stop right about there. But you get the idea of how this works, right? So that's the ability to point your toes like that. And then the other joint is this one right here. and that goes like that, and so that's the ability to rock your foot side to side, right? I don't think I have the joint limits on there. Yeah, I can go all the way around. But that joint right there is side to side motion, right? I forgot to add the bolt holes there too. But I'm gonna stop for a second and just say something. If you look at this now, it should start to make sense how, there's gonna be a rubber sole that this thing gets attached to, sewn on with Kevlar and then glued to is how I did mine. I just haven't modeled it yet, but there's a bunch of holes that are going this to allow it to go together. So there's this big rubber shoe that you're standing on, but it should be evident now that also the suit is standing on its own foot, which is really cool because you'll literally be able to put this thing on and it'll weigh, I think it weighs 250 pounds is about what it's gonna weigh. It's pretty heavy, but you literally won't feel the weight. You'll feel it when you're moving and stuff, but you literally won't feel the weight when you're standing in it because it'll stand on its own feet, which I just think is the coolest thing in the world. But yeah, it's pretty cool. So that, and I can tell you from wearing my suit that that's actually how it feels. And the very last joint we're gonna look at here is the toes. So if I put me back in the suit, there's James's toes, my toes. It goes up and down like that. And so the movement of this is pretty small, especially when you get it attached to the rubber that's underneath. That by the way is gonna be, the way I did it is I 3D printed a mold and then I poured on product from Smooth On, an epoxy silicone. And then and then pulled it out of the molds, and then it had the through holes and everything you needed in there, and then just sew it right on. Worked pretty well. So yeah, the leg is cool because it shows you how the load is going to transfer to the ground. Other than that, you know, the leg is kind of bulky and big and stuff, but yeah, it's pretty cool, huh? Oh, there will be also another support that comes in kind of this way, which is, or potentially just from the rear. That's how I did it on my suit as well, and that will also have, if assuming this is going to be actuated, which it should be, it will also have to have some pressure sensors just in the front and back since there's no rotation. My camera just stopped recording because it hit a time limit, so that's not a good sign about this video being short. It's the last one though. What was I saying? Oh yeah, so we'll need to know position control for that. So if you're pushing forward, it gets a pressure on the front, and then it's like, okay, open the leg up. And then if you're pulling back with your leg, getting pressure in the back, okay, flex the knee. So that's how that control will work. So, which is exciting. My suit, it was more of a study in like, can I build this and can I make something awesome looking? But I never really expected to really be able to power it. But this is awesome because it's actually going to be powered, which is going to be really, really cool. I'm very excited to see it. Hope you guys are excited to see it. I appreciate all 100 of you guys or so that are watching this, including James. I really appreciate you, man. And I'm excited to build this. Yeah, and that's all I got for you guys. Love you. Bye.